Good morning, everyone. The study of mathematics, like the Nile, begins in minuteness but ends in magnificence, says Charles Caleb Colton. The study of mathematics, like the Nile, begins in minuteness but ends in magnificence, says Charles Caleb Colton. On behalf of the Department of Mathematics, Holy Cross College, Autonomous Nagercoil, I, Sister Antin Mary, extend a very warm welcome for the state-level webinar on distances and algorithms in graphs. Let me offer a special welcome to our Vice Principal, Dr. Sister Lima Rose, to eminent resource persons, Dr. Titus, Head of the Department of Science and Humanities, University College of Engineering, Nagercoil, and Dr. Anto Kinsley, Associate Professor, St.Xavier's Autonomous College, Palayamkottai. My warm welcome extends to Dr. Arulfla, Head of the Department of Mathematics, motivating force behind all the department activities. I extend a warm welcome to the faculty members and students of our college and the other colleges. Wish you moments of awakening and learning. Go down deep enough into anything and you will find mathematics, says Dean Skeletor. We shall begin our webinar with the blessings of the Almighty as we prayerfully listen to this hymn. May I now invite Dr. Arulfla, the head of the Department of Mathematics, a person of vibrance, leadership, and meticulous planning, to give the welcome address.
Good morning to all. It's a pleasure to welcome everyone for our department webinar today. First, First, I extend a warm welcome to our loving Vice Principal, Dr. Sister Lima. The first thing which flashes across the mind is the courage, concern, and love she has for the poor, sick, and needy. In the midst of the terrible second wave of COVID 19, we saw her distributing food packets in the government hospital. That needs courage, concern, and love, and it speaks a lot about her. We should learn from her, and I feel proud and happy to welcome her in our midst today. Welcome, Sister. Dr. Titus is a well known researcher in graph theory. At present, he is working as Assistant Professor of Mathematics in the University College of Engineering, Nagercoil. He has the history of being the best student of mathematics in college and has received the Venus International Research Award for 2017. He has produced 4 PhDs at this young age and is guiding 8 scholars at present. He has written 5 books and has published 54 papers in international and 4 in national journals. He also has a DST project to his credit. He has been the member of different committees in the university level, such as Teaching Fellow Interview Team, Affiliation Inspection Team, Academic Audit Team, Advisory Committee, Selection Committee for Research Supervisors, Selection Committee for Scholars, Selection Committee for Teacher Fellowship, Squad Member of Anna University Examinations, and External Expert of PhD Viva OC Examinations. He has served in various capacities such as Deputy Controller of Examinations of Anna University of Technology, Tirunelveli, Head of the Department of Mathematics, University College of Engineering, Tirunelveli, Head of the Department of Mathematics, University College of Engineering, Nagercoil, and Chairman of the Mathematics Board of Anna University Valuation. He has also served as the Board of Studies member of various colleges like Anna University Chennai, Anna University of Technology Tirunelveli, St.Xavier's College Palayamkottai, Nurul Islam College, and MEPCO Slunk Engineering College Sivagasi. As a person, he is sincere and honest, who is also very helpful to his financially poor students. On behalf of myself and everyone present here, I accord to you, sir, a very warm welcome.
Thank you, ma'am.
A warm welcome to Dr. Anto Kinsley too, who is the resource person for the second session. I also welcome the faculty and students from other institutions and my own colleagues and students. Welcome one and all. Thank you.
Thank you, ma'am, for your warm words of welcome. May I now request Dr. Sister Lima Rose, our Vice Principal, an Assistant Professor of Botany, a person with far-sighted vision and practical sense, to felicitate the event.
Honorable Secretary and Principal, renowned resource persons Dr. Titus and Dr. Anto Kinsley, Convener and Head of the Department of Mathematics Dr. Arulflar Mary, Organizing Secretaries Dr. Magila and Dr. Sister Antin Mary, respected professors, scholars and students. A pleasant good morning to all. I am profusely elated to take this opportunity to offer my felicitation for the state-level webinar on distances and algorithms in graphs. To motivate others, we need to inspire by our commitment, competence, and hard work. Yes, dear participants, the Department of Mathematics always aspires to reach high. For that, they work hard, spend time and energy, and achieve success everywhere. I appreciate Dr. Arulflar Mary for the encouragement and the support provided to the staff and students to reach their goal. I do appreciate the organizing secretaries, Dr. Magila and Dr. Sister Antin Mary, for their interest and enthusiasm in providing excellent knowledge to the students and faculty and for their efforts in organizing this meaningful and effective webinar. Along with them, I wish to appreciate the faculty of the Department of Mathematics who are the backbone for the success of this webinar. Congratulations to all. I am also happy with the choice of the resource persons, Dr. Titus and Dr. Anto Kinsley, who consented to be amidst us in online mode to share their knowledge and experiences. Let us be enriched through their presentation and obtain good knowledge on distances and algorithms in graphs for better understanding of the concepts. Life is uncertain and full of challenges. Let us equip ourselves with knowledge technologically and accept the challenges. At this juncture, I would like to congratulate and extend my sincere appreciation to the Department of Mathematics for releasing their annual newsletter. I am sure it is the sincere efforts of each member of the department and the editorial team which made this come true. Congratulations once again. This webinar allows for better understanding of mathematical concepts and bring together professors, scholars, and students on an equal platform. I am sure that this webinar will be extremely beneficial and fruitful for everyone present here. Wishing you all the very best. Thank you.
Thank you, sister, for your felicitation. Due to her busy schedule, sister will leave the meet shortly. So we shall now proceed with the release of annual newsletter of the department. Usually, newsletter is released during our college day function. It wasn't possible due to COVID. So may I now, on behalf of the Department of Mathematics, take the privilege of releasing the annual newsletter 2019-20. Department of Mathematics, Holy Cross College, Autonomous Nagercoil, proudly releases its annual newsletter 2019-2020. So this newsletter carries a message from the head of the Department of Mathematics, Dr. Arulfla Mary. And the best outcome students are portrayed, rank holders of French, Tamil and English. The events like Board of Studies, National Seminar organized, and Sister Scholastica's and Mrs. Krishnamal's endowment lecture arranged. And our faculty has served as resource person, and we have achieved 100% results. These are all the activities related to research. Staff and students attending webinars, seminars and publishing papers. And Jenny Sioni of 3rd BS Mathematics was selected as Vice President of the College Students' Council. 10 of our students were motivated to compile their short stories and poetry as a book named Kottamuthukal. And Mathletes is a quiz club which motivates the students to participate in the quiz competitions and various other mathematical related competitions inside and outside of our college. So our girls have won so many prizes, and students also involved in various other activities and by participating in many competitions organized inside and outside of our college, and they have bagged many prizes. Our students are the proud winners of the Rolling Trophy for the College Fine Arts Competition. And they have bagged many prizes. Few of our final year students were selected in the campus placement, and our students involved in run activity that is reaching the unreached neighborhood. So, they had adopted a village, North Surangudi. They gave an awareness program. They could also involve in cleaning and planting. Activities of the Mathematics Association were carried out very successfully with the help of staff advisors and the student representatives. Many programs were organized, and in few programs our students were the resource persons. Final year students to Mysore and Bangalore and for the industrial visit to Priyadashini Planetarium. Bhargav, your third BSc, is the proud winner of many prizes in chess in the national, state, and district level competitions. And we organize Freshers' Day and students celebrate Teachers' Day. Collaborative work is well carried out in our department, and we are 11 faculty members. And the editorial board team members. Thank you. Thank you, Sister Lima, for spending your precious time and felicitating the event. On behalf of the Department of Mathematics and now all the participants of this webinar, we offer our gratitude to you. Thank you, Sister.
Thank you.
Thank you, Sister.
The participants are free to ask any doubts or questions from the speakers by typing them in the chat box on YouTube. Participants in Google Meet are free to ask your doubts or questions from the respective speakers once their session ends. May I now hand over the session to our eminent resource person, Dr. Titus, Head of the Department of Science and Humanities, University College of Engineering, Nagercoil. Please, sir.
Thank you, sister. Good morning to all. I'm very happy to meet you through this Google Meet platform. For that, first of all, I wish to thank the head of the Department of Mathematics, Dr. Arul Flower Mary, and the conveners of this webinar, Mrs. Magila and Sister Antin Mary, for giving me this opportunity. Also, I extend my sincere thanks to the management of this institute and the faculty members of the Department of Mathematics, Holy Cross College, Nagercoil. In this talk, I'm going to share something about the topic distances in graphs. After that, my professor, Dr. Anto Kinsley, sir, is going to share about the algorithmic aspect related to distances in graphs. Okay. Now, for our convenience, I can split my presentation into 5 parts. They are, first one is introduction, second one is distance. Distance means that is based on the usual distance. That means that is based on the shortest path. Third one is D2 distance. That is based on the longest path. And the fourth one is monophonic distance. That is based on a cordless path. And the last one is conclusion. Okay. So first part is introduction. Nowadays, graph theory plays an important role in mathematics research. Distance is one of the most important concepts of distance in graph theory. Okay. To illustrate the basic concepts related to our topic, we just consider the graph G shown in the figure. Okay, I think all of you know the definition of path, isn't it? Okay, so I assume all of you know the definition of path. Okay, using that assumption, I proceed my presentation. So just we take 2 vertices x and y. Now just we collect all possible paths joining the vertices x and y. Okay. So can you give a path joining the vertices x and y? Okay, I can give the path. So the first path joining the vertices x and y is x, u1, u2, u3, y. Then the next possible path joining the vertices x and y is x, v, y. Then we have another path joining the vertices x and y is x, a, b, y. Okay, then can you give one more path joining the vertices x and y? Yes, we can. We have another path joining the vertices x and y is x, w, y. Now, is there any other path joining the vertices x and y? No. So we have only 4 possible paths joining the vertices x and y. They are P1, P2, P3, and P4. Okay. Out of the 4 paths, we have 2 paths are shortest paths. Shortest path means based on the length of the path, we can say shortest path. Okay. So length means number of edges in a path is length. Okay. Number of edges in a path is length of the path. Okay. Now for the first path, the length is 4. For the second path P2, the length is 2. For the third path, the length is 3. For the fourth path, the length is 2. So here we have 2 shortest paths, P2 and P4. Hereafter, we can call a shortest path as geodesic. So geodesic is the technical word of shortest path. So hereafter, instead of calling this shortest path, we can say that is a geodesic. Okay. So here P2 and P4 are geodesics. Similarly, we have one longest path, that is P1. This is the longest path, okay, having the length 4. Okay, so hereafter we can call this longest path as detour. Okay, detour is the technical word of the longest path. So P1 is the longest path, that is detour, and P2 and P4 are the geodesics. Okay, then now second topic is distance. Okay, so the distance, the first one is the definition. The distance between 2 vertices U and V is the length of an U to V geodesic, and it is denoted by the symbol D of U comma V. So the notation for the distance between the 2 vertices X and Y is D of U comma V, and it is nothing but a distance means just the length of the U to V geodesic. Okay, or we can rewrite that as length of a shortest U to V path, or we can rewrite that as the number of edges in a shortest U to V path. Okay, so these are the different types of the definitions of distance. Okay, distance means just we can identify the number of edges in the shortest U to V path, or number of edges in the U to V geodesic. Okay, now next one gives the boundaries of the parameter D of U comma V. Okay, so all of you know distance is always non-negative. Distance is always non-negative. That means D of U comma V is greater than or equal to 0. And again, here we can use this is a path. This D of U comma is based on the geodesic, that is based on a path. So in a path, we have at most P minus 1 edges. In any graph, we can take a path having only P up to P minus 1 edges. So here the upper bound of the distance D of U comma B for any 2 vertices U and B is P minus 1. Therefore, this distance lies between 0 and P minus 1. Okay, so 0 and P minus 1 are the bounds of the distance, usual distance D of U comma V. Okay, now the bounds are sharp. That is, for the bounds, so here in the previous result, we have the bound, a lower bound for the distance D of U comma V is 0, and the upper bound for the distance D of U comma V is P minus 1. Okay. Now here there exists a connected graph G with the lower bound which satisfies the lower bound D of U comma V equal to 0. Similarly, it satisfies the upper bound D of U comma V equal to P minus 1. For that, just we consider a path having 5 vertices, that is P5. So in P5, we have 5 vertices and 4 edges. Now here, if I take the vertices are U and V, that is just to take U and V are the end vertices of the path P5. Okay, now what's the length of this path? That is, what is D of U comma V? D of U comma V is the number of edges in a U to V geodesic, or number of edges in a shortest U to V path. So here we have a unique path. Here the number of edges is 4. So the distance between U and V is 4. That is D of U comma V equal to 4. Okay, and the number of vertices here is 5. 1, 2, 3, 4, and 5. So P equal to 5. So we have D of U comma V equal to 4 equal to P minus 1. Okay, hence we have this D of U comma V satisfies the upper bound P minus 1. Now for the lower bound, if I take the vertex W, just to take W, and we treat this W equal to U and W equal to V. So U equal to W and V equal to W. So what is the distance between D of U comma V? D of U comma V means, just to take the vertex W. So D of U, here we assume the value U equal to W and V is also W. So we have D of U comma U equal to D of W comma W equal to the number of edges in the W to W path. Here there is no path joining the vertices W and W. So number of edges here is 0. Therefore, we have d of w comma w equals 0. Or here we assume the value u equal to w and v equal to w. Therefore, we have d of u comma w v equal to 0. Okay. Now, the next one is distance is a metric. Okay. So to prove the distance d of u comma is a metric on the set of vertices v, okay, it is enough to verify the 4 conditions of metric. So the first condition is d of u comma v is non-negative, that is greater than or equal to 0. Already we have all the vertices, all the distances are positive, always positive. Therefore, we have d of u comma v greater than or equal to 0. Then the second one is reflexive property. Reflexive, that is d of u comma v equals 0 if and only if u equal to v. Okay. If I take the first direct part, that is if d of u comma v equals 0, then we have the geodesic from u to v has no edges. That is the number of edges in the u to v geodesic is 0. That is the number of edges in the u to v path is 0. That means there is no path joining the vertices u and v. There is no path joining the vertices u and v means we assume that u equal to v. Otherwise, this gives a contradiction because we assume this G is a connected graph, a simple connected graph. In a connected graph, for any 2 vertices, there is a path. There exists a path. But here there is no path joining the vertices u and v because we have d of u comma v equal to 0. Therefore, we have the value u equal to v. Okay, so the converse part. In the converse part, if we assume the value u equal to v, then we can easily derive the value d of v comma v equal to 0. Already we derived that result using an example, that is using the path P5. Okay, then the third one is symmetric property. That is d of u comma v equal to d of u comma v equal to d of v comma u. That is just we interchange the notations u and v. Okay. Now here, if I take d of u comma v, here we have one u to v geodesic. That is the number of, we know that the number of edges in an u to v geodesic is same as the number of edges in a v to u geodesic. Okay, just we change the order, that's all. Okay, so the path is the same path, the geodesic path is the same path. So the number of vertices from u to v and the number of vertices from v to u are the same. Therefore, the distance between these two are same. Hence, we have the symmetric property. Okay. Then the fourth one is triangular property. That is d of u comma v less than or equal to d of u comma w plus d of w comma v. Okay. So to prove this triangular inequality, just we consider 3 vertices u, w, and v. Okay. Already we have in the right side we have a part d of u comma w. That means the distances between u and w. From this distance, clearly there exists a u2 and u2 w geodesic. Okay, there is u to w geodesic. For our convenience, I take this P1 as a geodesic joining the vertices u and w. Okay, so this is the path P1. This is the geodesic joining the vertices u and w. Then based on the second part of the right side, d of w comma v, we assume another path P2 from w to v. So here P1 and P2 are the 2 geodesics. Okay. Now, if I combine these 2 geodesics, P1 and P2 at the point W, just we join these P1 and P2 at the point through the point W, then we get another path from U to V. So P1 union P2 is a path. This path need not be a geodesic. Already we have the segments P1 and P2 are geodesics. But if we combine these 2 through the point or at the point W, then we get another path. Clearly, this is a path. This path need not be a geodesic. Okay. Okay. So here we have 2 cases based on this new path P1 union P2. If P1 union P2 is a geodesic, okay, this may be a geodesic. Okay. So if P1 union P2 is a geodesic, then we have this d of u comma v is equal to d of u comma w plus d of w comma v. Okay, if we combine these 2, that is the length of this P1 union P2. Then the second case is P1 union P2 is not a geodesic. Okay, that is this P1 union P2 is a path, but this need not be a geodesic. So here we assume the second case is P1 union P2 is not a geodesic. Okay, if P1 union P2 is not a geodesic, then clearly there exists another geodesic, say P, another geodesic from U to V. So let P be a geodesic from U to V. Okay, now here we have one length, isn't it? So the length of P is clearly strictly less than the length of P1 union P2. So because this P is a geodesic and P1 union P2 is not a geodesic. That means when we compare the length of P with P1 union P2, clearly the length of P is strictly less than the length of P1 union P2. Okay, from that we have D of P means D of U to V, U comma V is strictly less than P of D of P1, that is D of U comma W, plus D of P2, that is D of W comma V. So if we combine these two cases, that is our required result, D of U comma V is less than or equal to D of U comma W plus D of W comma V. Okay, this is the third property. And the fourth one. Okay, so hence we have all the four properties of this metric is satisfied. Hence we conclude that the distance, usual distance small d, is always matrix on the vertex set V. Okay. Now here we have, based on the usual distance, we have three standard and important parameters. First one is based on the vertex, and the remaining two parameters are based on the graph. Okay, so here we have three parameters. First one is based on the vertex of a graph, that is E of V, and the remaining two parameters are based on the graph. Okay, so the first one is eccentricity of a vertex V in a graph G. The eccentricity is denoted by the symbol E of V, and it is defined as the maximum of the distances from V to any other vertex U in V. Okay, we define the eccentricity as E of V equal to maximum of the distances from V to all the remaining vertices in V. And using this eccentricity of a vertex, we can define the radius of the graph G. Radius of graph G is defined as the minimum of the eccentricities taken over all the vertices in the graph G. Okay, minimum of the eccentricities for all the vertices in the graph G. Okay, then in the same way we can define the diameter as diameter of G is denoted by diam G, and it is defined as the maximum of the eccentricities among all the vertices of the graph G. Okay, so these are the very important parameters. Okay, these are the very important parameters. Based on these three important parameters, we have so many results and properties in the literature. Okay, you can refer all these parameters in our textbooks and in the reference papers also. Okay, then the main topic is geodomination. Geodomination is one of the most important concepts of distances in graphs. The geodetic sets and the geodomination number of a graph were introduced and studied by Buckley, Harare, and Quintas in the year 1988. Since then, many related concepts and interesting results were developed and studied by many others from different countries. However, Chartrand and Chang have done a tremendous work in this area. Okay. In India, my guide, Dr. A.P. Sandakumaran, have done a tremendous work in this area. Okay. You can refer these data using the papers. Okay. The next one is the definition of geodomination number. This is a very important parameter in distance in graphs. So geodomination number, or another name of this is geodetic number. So the first introduced notation for the number is geodomination number. Afterwards, it is renamed as a geodetic number. Okay. The definition is, let G be a connected graph. A set S of vertices of G is called a geodominating set if every vertex of G lies on an X to Y geodesic for some vertices X and Y in S. The minimum cardinality among the geodominating sets is called the geodomination number, and it is denoted by the symbol G of G. A geodominating set of cardinality G of G is called a G set. Okay, so once again read this. Geodominating set. Geodominating set is a subset S of the vertex set V, satisfying the condition every vertex of G lies on next to Y geodesic for some vertices X and Y in S. Okay. Every vertex of G lies on an X2Y geodesic for some vertices X and Y in S. So to illustrate this concept, we consider the graph G shown in the figure. Okay. Now here the problem is just find the geodomination number for the graph G given in the figure. Okay. To find the geodomination number, we need geodominating set. But to find the geodominating set, we need geodesic. But to form a geodesic, we need two vertices. So we can start with the 2-point set. If I take the 2-point set as X, Y, okay. Now to verify the conditions for this geodominating set, first identify the geodesics joining the vertices X and Y. So here we have 3 geodesics joining the vertices X and Y. This is a geodesic joining the vertices X and Y, and this is another geodesic joining the vertices X and Y. Similarly, this is a third geodesic joining the vertices X and Y. But this path is not a geodesic. Okay. Now here, from this geodesic path, we conclude that the vertices X, U, and Y lie on this X2Y geodesic. Similarly, the vertex V also lies on this geodesic. In the same way, the vertex W also lies on this geodesic. But what about the points A and B? So clearly, these two vertices, that is the vertices A and B, do not lie on any geodesic joining the vertices X and Y. So clearly, the 2-point set X, Y is not a geodominating set. Okay. So then we can go for another 2-point set. If I take the another 2-point set as U, W, then here also verify the conditions. Here the vertices U, X, and W lie on this geodesic. Similarly, the vertex Y lies on this geodesic, but the vertices V, A, and B do not lie on any U to W geodesic. Therefore, this 2-point set U, W is also not a geodominating set. In the same way, we can easily verify that no 2-point set will form a geodominating set. So we can go for a 3-point set. If I take the 3-point set as this X, Y, A. Now clearly, every vertex of G lies on either an X2Y geodesic or a Y to A geodesic. Clearly, the vertices X, U, and Y lies on this geodesic. The vertex V lies on this geodesic. This W lies on the geodesic X to Y, and the vertices A and B also lies on this Y to A geodesic. Therefore, the 3-point set X, Y, A is a geodominating set of G. Since this is a geodominating set with the minimum cardinality, we can say this is a G set. Minimum geodominating set is called a G set. So this is a G set. And also we can identify the geodomination number G of G as 3. Minimum cardinality, that is 3. Okay. Now this is a geodominating set with the minimum cardinality, this is a G set. Now can you identify one more path, one more G set? We can easily identify another geodominating set as this X, Y, B. Clearly, every vertex of G lies on either an X2Y geodesic or an X2B geodesic. Therefore, this 3-point set X, Y, B is also a G set. Okay. So from this definition or from this example, we can conclude one result as G set need not be unique. G set need not be unique. So we have 2 or more G set. Okay. Now here we have some properties. We have some properties of this geodominating sets. Okay. So to prove the properties of geodominating set, we need these 2 terms, or we need these 2 definitions. First one is neighborhood. Second one is simplicial vertex. Neighborhood. So the definition is the neighborhood of a vertex V is the set N of V consisting of all vertices U which are adjacent with V. The meaning of this is the notation for the neighborhood of V is N of V, and this N of V is a set containing all the adjacent vertices of V. collection of all adjacent vertices of V gives enough V, that is neighborhood of V. Then next definition is a vertex V is called a simplicial vertex or extreme vertex if the subgraph induced by its neighbors is complete. Okay, so to verify whether the vertex is simplicial or not, we can check two conditions. First one is first identify the neighborhood of the vertex V, then verify whether the induced subgraph of V is simply complete or not. If the induced subgraph is complete, then we say that vertex is a simplicial vertex or extreme vertex. Okay, so for that, just we consider this example. So this is a graph, and here take a vertex V1. Now identify the nature of the vertex V1. That is, verify whether the vertex V1 is simplicial or not. So to verify the nature of this vertex V1, first we can identify the neighborhood of the vertex V1. Neighborhood means set of all adjacent vertices of V1. So set of all adjacent vertices is the 2 points at V2, V3. And the second condition, its induced subgraph is complete. Now, what is the induced subgraph of the vertices V2 and V3? Clearly, it is a complete graph K2. This is an edge V2, V3. So clearly, that is equivalent to K2. So the induced subgraph of the neighborhood of V1 is complete. Therefore, we can say this V1 is a simplicial vertex or extreme vertex. Now, what about the vertex V4? V4, again, to verify the nature V4, so identify its neighborhood. The neighborhood of this vertex V4 is V2, V5, V2, V5, and its induced subgraph in G is this vertex V2, that is K1, union another vertex V5, that is K1. So K1 union K1. So K1 union K1 is clearly not a complete graph. So the induced subgraph of V4 is not complete. Therefore, we can say this V4 is not a simplicial vertex. Okay. Then what about the vertex V7? V7, you can verify this. So V7, its neighborhood is V6. V6, its induced subgraph is the complete graph K1. Here we have only one vertex. So its induced subgraph is K1. That is a complete graph. Therefore, V7 is also a simplicial vertex. Okay. Now, from this example, we have one result. Okay. Every end vertex is a simplicial vertex, but the converse need not be true. Every end vertex is a simplicial vertex, but the converse need not be true. Okay. So already we have, this is an end vertex. End vertex means its degree must be 1. So clearly it is an end vertex, and it is a simplicial vertex. So every end vertex is a simplicial vertex, but a simplicial vertex need not be an end vertex. Already we have this V1 is a simplicial vertex, but it is not a end vertex. Okay. So we have that result. Every end vertex is a simplicial vertex, but the converse need not be true. That means a simplicial vertex need not be an end vertex. Okay. So using these two definitions, we can prove this theorem. There's a very, very important property of geodominating set. Here, every simplicial vertex belongs to every geodominating set of G. That is, if we take A is a simplicial vertex of the graph G, then clearly this A is an element of any geodominating set of G. Then the second property is no cut vertex of G belongs to any G set of G. G set means minimum. Here we have geodominating set, any geodominating set, but here we have the concept based on the minimum geodominating set, that is G set. So no cut vertex belongs to any G set or any minimum geodominating set of G. So here for the proof, just I give a skeleton. Okay, I give a skeleton of the proof. Okay, so just to consider a graph G, let S be a geodominating set of G. We consider S is a geodominating set of G, and let U be a simplicial vertex of G. Here we are going to prove the result U is an element of S. U is an element of S. Now here we can use the method of contradiction. So in mathematics, we have one important technique is method of contradiction. So here we can use the method of contradiction. Okay. Here, if suppose that U is not in S, U is not an element of S, then what will happen? S lies outside the set S. Uங்கிற இந்த vertex வெளியே வந்திருக்குது அப்படிதானே? U is not in S. Then using the definition of the geodominating set, since U lies outside the set S, okay, there exist at least two vertices X and Y in S such that U is an internal vertex of this X to Y geodesic. Okay, using the definition of geodominating set, since U lies outside the set S, clearly U lies on an X to Y geodesic. Okay, so here we have one geodesic. Okay, now here let V and W be, let V and W be the neighboring vertices of U on the path P, on the geodesic P. So already we have this X to Y geodesic. Since U is not equal to X and not equal to Y, there exist at least two vertices V and W along the path P. Okay. Now here again use the definition of this U, simplicial vertex. Okay. What is the definition of simplicial vertex? Its neighborhood is complete. The initial subgraph of the neighborhood is complete. Its neighborhood is complete means its neighboring vertices are adjacent. So here V and W are the adjacent vertices of U. So they must be adjacent. They must be adjacent means there exists an edge between V and W. So here we have an edge V to W. Okay. After taking this this edge VW, then we have a new path from X to YS, X to W, then the edge WV, then the path V to Y. So this is a new path. That this is a path other than P. Okay, so it is P1. So second path P1 is X to W, then the edge WV and the path V to Y. V to Y. Okay, now when we compare the length of P with P1, clearly the length of P is greater than the length of P1. Okay, length of P is greater than the length of the new path P1, because here we have two edges. In the path here we have two edges. Okay, corresponding to this two edges in P1 we have a single edge. So clearly the length of the path P is greater than the length of P1, or the length of P is equal to the length of P1 plus 1. Okay, so hence we have another geodesic. Okay, which is a contradiction to the path P is a geodesic. Okay, so we derived a contradiction, hence we have the result. Every simplicial vertex belongs to the set S. Okay, so this is just the outline of the proof. Okay, in the same way we can do the second one, just I skip that one. Then the next one is vertex geodomination number. Actually the parameter geodomination number is defined in the sense of there is exactly one geodomination number for a graph. Okay, so corresponding to a graph G, we have only one number parameter, that is geodomination number. In the year 2005, we means myself and my guide Dr. A.P. Sandakumaran defined and developed the concept of geodomination by fixing a vertex of a graph. Okay, that is with respect to each vertex of a graph G, we define a corresponding geodomination number. Thus, the new parameter vertex geodomination number is based on, okay, based not only on the graph but also based on the vertex of a graph. Okay, so corresponding to each vertex of a graph, we have a parameter. Okay, so its the definition is, let X be any vertex of a connected graph G. A set S of vertices of G is called an X geodominating set if every vertex of G lies on an X to Y geodesic for some vertex Y in S. Similar to the previous one, the minimum cardinality among the X geodomination set gives the geodomination number, that is X geodomination number, and it is denoted by the symbol Gx sub G or simply Gx. An X geodominating set of cardinality Gx sub G is called a Gx set. Okay, so X geodominating set is based on each vertex of a graph G. Here, the main difference between geodominating set and the X geodominating set is, so in the geodominating set we have X to Y geodesic. Okay, that is in the X to Y geodesic X and Y may vary, but here in the X to Y geodesic X is fixed. That is the initial point of the geodesic is fixed. That is the main difference between the usual geodominating set and the vertex geodominating set. Okay. Okay, to illustrate this concept, consider the graph G shown in the figure. So in this figure, okay, already we have the geodominating set and the geodomination number. We can easily identify the geodomination number is 2 because the geodominating set is u comma y. If you take the 2-point set as u comma y, then clearly every vertex of G lies on either this geodesic or this geodesic. Therefore, the geodomination number for the given graph is 2. But here we are going to find the vertex geodomination number corresponding to each vertex of a graph G. For that, first I take the vertex as x. Okay. Now to find the x geodomination number, we need x geodominating set. For that, we need x to y geodesics. And here x is fixed. For all the geodesics, the initial value x is fixed. So it is enough to vary the upper limit y. Okay. So for that, here we start with a single point set. If I take the single point set as u, then what will happen? Here the vertices x, v and u lies on this x to u geodesic, but the vertices y and w do not lie on any x to u geodesic. Therefore, the single point set u is not a x geodominating set of G. So in the same way, we can go for the next single point set w. Here also the vertex u does not lie on any x to y, x to w geodesic. Therefore, the single point set w is also not a x geodominating set of G. In this way, we can easily verify no single point set will form a geodominating set. So we can go for a 2-point set. Here, if I take the 2-point set as this u comma w, then clearly every vertex of G lies on either an x to u geodesic or this x to w geodesic. Hence, okay, the 2-point set u comma w is a gx set and gx of G equal to true. Okay. In the same way, if I fix the vertex as u instead of fixing the vertex x, if I fix the vertex u, then the single point set y is clearly a GU set because every vertex of G lies on either this u to y geodesic or another u to y geodesic. Therefore, the single point set y is a GU set. Therefore, GU of G equal to 1. Okay. Then this table shows the vertices of the graph and its corresponding minimum vertex geodominating sets and its corresponding vertex geodomination numbers. So corresponding to each vertex, if I fix the vertex W, then we have the corresponding minimum vertex geodominating set and its corresponding vertex geodomination number true. Okay. In this way, here also we have so many properties related to this. Okay, you can refer these properties in the in the reference papers. Okay. Now here the next theorem is this. This is exactly similar to the previous one. So just to be omit this. Now related to this geodesic path and geodesic, okay, we have based on this usual distance, we have the geodomination number. Based on the geodomination number, we have so many related topics. The related topics are: first one is upper geodomination number, forcing geodomination number, connected geodomination number, upper connected geodomination number, forcing connected geodomination number, connected forcing connected geodomination number, edge geodomination number, etc. We have so many parameters related to this topic, geodomination number. Okay. Then similar to this vertex geodomination number also, we have so many parameters. We have so many new parameters. So the best parameter related to this vertex geodomination number is geo number. Okay. Similarly, we have the other parameters. Okay. So next topic is D2 distance. Okay. Actually, we have studied a distance based on geodesic, isn't it? The previous one is distance, that is usual distance, that is based on the geodesic. Okay. Then the next one is based on a longest path. Longest path means D2 path. Okay. So hereafter we can call a longest path as a D2. So you can remember a longest path is also called a D2. Okay, the D2 distance was introduced by Chorten, Escatro, and Chang in the year 1990. Okay, since then many related concepts and interesting results were developed by so many others from different countries. Okay, so to illustrate this D2 distance, we Okay, first we can define this detour distance based on the detour path. So the length of an U to V detour is called a detour distance, and it is denoted by the symbol capital D of U comma V. So already we have the usual distances small d of U comma V. Now here we have the detour distances denoted by the symbol capital D. So capital D of U comma V. Okay, and here the length of this U to V detour, or the length of a longest U to V path, is called the detour distance. Okay, to illustrate this concept, we can consider the graph G shown in the figure. Okay, so already we have, already we identified all the possible paths joining the vertices X and Y. So we have 4 paths joining the vertices X and Y. Out of the 4 paths, 2 paths are shortest paths, that is geodesic paths. So don't worry about that geodesic path. Okay, and we have 1 path that is a longest path, that is a D2. So longest path are D2. So here we have X to Y detour is this X, U1, U2, U3, and Y. Okay, this is the longest path. Okay, so we can say this is a D2. Okay, then here we can consider one more example. Now, can you identify the D2 joining the vertices U and V? U and V. Okay, so here we have 2 paths joining the vertices U and V. First path is this UV. Next path is UABY. So here the longest path is this UABV. So this is a D2. Okay. Now here we have some properties similar to the D2 usual distances. Okay. So similar to the previous one, D2 distance also lies between 0 and P minus 1. So the bounds for the distance D2 distances 0 and P minus 1. Bounds are 0 and P minus 1. Next one, this is also similar to the usual one. So D of U comma V equals 0 if and only if U equal to V. Then the next one is similar to the previous one. That is D2 distance is also a met on the vectors on the vertex set V. Okay. Next one is the relation between the distance and usual distance. Next one is the relation between usual distance and the D2 distance. Okay. Already we know that. Okay, already we know that the number of edges in a geodesic is clearly less than or equal to the number of edges in a D2 path. Okay, so that is when we compare the shortest path and the longest path. Okay, the number of edges in a shortest path is clearly less than or equal to the number of edges in a longest path. From that, we have the number of edges in a geodesic is less than or equal to the number of edges in a D2 path. From that, we have D of U comma V is less than or equal to capital D of U comma V. Already we know that these 2 parameters D and capital D lies between 0 and P minus 1. So from that, we have the result 0 less than or equal to D of U comma V less than or equal to capital D of U comma V less than or equal to P minus 1. Okay. Then the next one is in an even cycle 2n. We have D of U comma V equal to capital D of U comma V equal to n if U and V are 2 antipodal vertices of the graph G. If U and V are the antipodal vertices, then we have the usual distance and D2 distance are the same. This is only for an even cycle. Okay. So here if I take this as an even cycle, here we take 2 antipodal vertices U and V. This U and V are the antipodal vertices. Antipodal vertices means the eccentricity of U is equal to eccentricity of V equal to the distance between U and V. Eccentric E of U equal to E of V equal to D of U comma V. These 3 values must be same. Then only we say U and V are eccentric vertices. Now here we have 2 distinct paths joining the vertices U and V having the same length. We have only 2 paths having the same length. Therefore, the usual distance D of U comma V and the D2 distance capital D of U comma V are same. Okay, hence we have the result. Suppose U and V are not antipodal vertices. For example, if I consider U and V, clearly U and V are non-antipodal vertices. Then the distance between these 2 is 1 and the D2 distance between U and V is this 2n minus 1. Total number of vertices is 2n. So the d2 distance from u to v is 2n minus, we start from this, okay, and end with this u. That gives 2n minus 1 vertices. Okay, therefore d of small d of u comma v is not equal to capital D of u comma v. Okay, then the next one is d of u comma v equal to capital D of u comma v for every vertices u and v if and only if the graph G is a tree. This is another result based on a tree. Okay, so here also if I take the direct part as d of u comma v equal to direct part d of u comma v equal to capital D of u comma v for any two vertices u and v in G, then we prove that G is a tree. Okay, first we assume the value, this d of u comma v equal to capital D of u comma v for any two vertices u and v in G. Using that assumption, we can prove the result G is a tree. Here also we can use the method of contradiction. That is, if G is not a tree, then we are going to derive a contradiction. If G is not a tree, then G must contain at least one cycle. Okay, then G must contain at least one cycle. Suppose we have a graph like this. In this graph, we have a cycle like this. Now, in this graph, in this in this non-tree, that is a graph having the cycle, just we take two adjacent vertices u and v. Take two adjacent vertices u and v. Now, the usual distance between these two vertices is 1, and the d2 distance between u and v is 3. 1, 2, and 3. So clearly, d of u comma v is not equal to capital D of u comma v. That is a contradiction. Already we assume that is equal. So we derived a contradiction. Similarly, if we take G is a tree, converse part, if G is a tree, then we can prove the result d of u comma v equal to capital D of u comma v for any two vertices u and v. Okay, if G is a tree, then what will happen? If we take any two vertices, then we have exactly only one path joining the vertices u and v. Okay, here also if I take the vertices a and b, here also we have a unique path joining the vertices a and b. Okay, so we know that in a tree, okay, we have a unique path joining any two vertices in tree. Okay, therefore we have a unique path, means that path is geodesic, both geodesic and d2. For that we have small d of u comma v equal to capital D of u comma v. In that way we can easily derive that result. Okay, then the next one is, as usual, here we have d2 eccentricity. We can define d2 eccentricity, then d2 radius and d2 diameter exactly similar to the usual distance. Okay, then we have the next result is, now we have the comparison with the usual eccentricity with the d2 eccentricity. Since based on for any two vertices u and v in G, okay, d of u comma v is less than or equal to capital D of u comma v. Using that concept, the eccentricity of v is less than or equal to d2 eccentricity of v for any vertex v in G. Okay, using this eccentricity, and that is using this relation, we can easily derive the result as radius of G is less than or equal to d2 radius, and diameter of G is less than or equal to d2 diameter. So we can easily derive these from the previous results. Okay, now here very important concept is based on the neighbor. So already we have the usual neighbor, isn't it? Now here we are going to define d2 neighbor. Okay, so already we have studied this usual neighbor. Okay, what's the definition of this neighbor? A vertex is called a neighbor of v if, what is the condition? A vertex is called a neighbor of v if u is adjacent with v. If u and v are adjacent, then we say u is a neighbor of v or v is a neighbor of u. Or we have another definition as d of u comma v equal to 1. This is an equivalent form. U is adjacent with v means the distance between these two is 1. Okay. Or we have another definition as u is a vertex distinct from v whose distance from v is minimum. Okay. So the actual definition of the neighbor is this. Okay, so these two are the particular cases of this definition. So actual definition of a neighbor is this. Okay, I think many of you don't know this formula, isn't it? This definition, but this is a very important definition of neighbor. Okay, these two are the deductions, are the particular cases of this definition. Okay, the definition is U is a vertex distinct from V, that is U not equal to V, and its distance from V is minimum. Okay, so if you take this definition, from this we can easily derive this. So the V is minimum means we have at least one neighboring vertices, neighbor vertex gives the value D of U comma V equal to 1. So we can easily derive these two from this. Okay, now using this definition of neighbor, we can define the D2 neighbor. So the next definition is a vertex U is called a D2 neighbor of V if U is a vertex distinct from V whose D2 distance from V is minimum. Instead of distance, here we have a D2 distance. Okay, U is a vertex distinct from V, that is U not equal to V, whose D2 distance from V is minimum. Okay, so here don't use the notation D of U comma V equal to 1. Okay, in the previous definition, we used the notation D of U comma V equal to 1. Okay, don't use this definition here. Okay, so the only definition based on this D2 neighbor is this. U is a vertex distinct from V whose D2 distance from V is minimum. Okay, now to explain this, just consider the graph G shown here. Okay, here identify the D2 neighbor of the vertex V. Fix the vertex V. Now identify the D2 neighbor of the vertex V. Okay, so to find the D2 neighbor of the vertex V, just we can identify the D2 distances from V to all the remaining vertices in the graph G. Okay, so first identify the distances. So what is the D2 distance from V to U? So here we take the path as this. Along this path, we have the D2 distance is 6. Then the D2 distance from V to Z is, take this path. Along this path, we have, the distance is 4. So capital D of V comma Z equal to 4. Then capital D of V comma W equal to 3. In the same way, D of V comma X, take this path. Along this path, we have capital D of V comma X equal to 4. And D of V comma Y equal to 5. Okay, out of these distances 3, 4, and 5, the minimum distance is 3. Corresponding to the distance 3, we have the vertexes V, so W. Therefore, the vertex W is a D2 neighbor of the vertex V. So you can remember this. Here, W is the D2 neighbor of V. So what is the neighbor of V? Here we have the neighboring vertices of V are U and Y. But the D2 neighbor of the vertex V is W. This is not U. So இதுக்கு பக்கத்துல இருக்குன்னு அது நைபர்னு சொல்ல முடியாது. D2 neighbor, that is based on the longest distance. Okay, that is the D2 neighbor as W. Okay, then if I take the next one as this V. So here we consider this odd cycle. Previous one is even cycle. Here we consider an odd cycle. Here also to find the neighboring vertices, first we can find the D2 distances from V to all the remaining vertices. So if I take the vertices V and U, then the D2 neighbor of D2 distance from V to U is 1, 2, 3, 4. So 4. Then the D2 distance from V to Z is 3. D2 distance from V to X is 3. D2 distance from V to Y is 2. So among the distances 2 and 3, okay, 2. Sorry. So here the distance from V to U is, along this path we have 4, isn't it? So the D2 distance from V to U is 4. The D2 distance from V to Z is 3. The D2 distance from V to X is 3. The D2 distance from V to Y is 4. So we have two distances, 3 and 4. Okay. Among these 3 and 4, we have the length, minimum length is 3. So based on the length 3, we have the D2 neighbors are X and Z. So the D2 neighbors of the vertex V are X and Z. Okay. In the same way, can you identify the D2 neighbor of the vertex V? So vertex V D2 neighbor கண்டுபிடிக்க முடியுமா? So the D2 neighbor of the vertex V is, here also find the distance, D2 distances from V to all the remaining vertices. Here the D2 distance from V to U is 4. The D2 distance from V to Z is 3. The D2 distance from V to X is again 3. The D2 distance from V to Y is 4. but the D2 distance from V to W is only 1. So the minimum length is 1. Based on that length 1, we have the D2 neighbor of V is W. So the D2 neighbor of the vertex V is W. So in this way, we can easily identify the D2 neighbors of the vertex X. So here D2 neighbor is entirely different from the usual neighbor. Okay, you can remember that one. Okay. Then we have one parameter based on the D2 number, D2 distance. Okay, that parameter is D2 number. Actually, the D2 number of a graph was introduced by Chorten and Chang in the year 2003 and further studied by many others from different countries. So usually, okay, actually this parameter was introduced by Chorten and Chang in the year 2003. Okay. Now here the definition of the D2 number is this is similar to the geodominating set. Okay. Here let G be a connected graph. A set S of vertices of G is called a D2 set. If every vertex of G lies on an x2y D2 for some vertices x and y in S. The minimum cardinality of a D2 set is called the D2 number and it is denoted by the symbol Dn of G. The minimum D2 set is called the Dn set. Already we have the notation for the minimum geodominating set is G set. Similar to that, we have the minimum D2 set is called D set, Dn set. Okay. Here, instead of taking the geodesic paths, here we consider D2 paths. That's all. Okay. Here we just take the graph. Now here find the D2 number of this graph. To find the D2 number of the graph, we found the sets. Okay, so to here we consider a 2-point set. If I consider 1-point set, then there is no path joining the vertices x to x. So we start with a 2-point set. If I take the 2-point set as x comma y, x comma u, first one is x comma u, then what will happen? Okay, here the vertices, here first identify the path. So this is a path, this is one of the paths joining the vertices x and y, and this is another path, and this is a third path joining the vertices x and u, and similarly we have the fourth path is this. Okay, out of these 4 paths, we have only one path is a detour path. That is, along this path, we have a detour. So this is a detour path. Okay, so here the vertices x, a, b, y, and u lies on this x to u geodesic path. Along this detour path. So the vertices v and w do not lie on any x to u detour. So clearly the 2-point set x comma u is not yet D2 set of G. So in this way, we can take the next 2-point set. If I take the next 2-point set as x comma a, now here we have the paths are this is a shortest path and the longest path is this. That is the detour path is this. Similarly, this is another detour path and the third detour path is this. So here all the vertices of the graph G lies on an x to a detour path. All the vertices lies on an x to a detour path. Therefore, the 2-point set x comma a is a detour set of G. Since it is of minimum cardinality, we can say this is a Dn set. And Dn of G equal to 2. Here also we have the other Dn sets also. You can verify that one. Okay. Now here also we have a theorem based on so one of the properties. Every end vertex of G belongs to every D2 set of G. Every end vertex. In the geodominating set, we have every simplicial vertex belongs to the geodominating set, but here end vertex of G belongs to every D2 set of G. Okay, just we can skip the definition proof of this. Okay, now here also we have so many parameters related to this D2 number. These are some parameters related to D2 number and D2 distance. Okay, then the next part is monophonic distance. Monophonic distance. Okay. Actually, we means myself and my guide Dr. A.P. Sandagamaran introduced this monophonic distance in the year 2011. And we developed so many parameters related to this monophonic distance. Okay, so this monophonic distance is based on a chordless path. For that, we need the definition of chord. Then, a chord of a path P is an edge joining two non-adjacent vertices of P. A chord means there is an edge satisfying this condition. A chord of a path P is an edge joining two non-adjacent vertices of P. That is, here we have one path. For example, suppose we have one path P. Now take two non-adjacent vertices. If the two non-adjacent vertices in P has an edge in G, then we say that is a chord. So பாத்துங்க ஒரு path இருக்கு, அந்த pathல non-adjacent vertices எடுத்துக்கங்க. அந்த non-adjacent vertices ஒரு edge graphல இருந்தால் அதை chord சொல்லலாம். Okay, so just consider a path and take any two non-adjacent vertices in P. If there exists an edge joining these two non-adjacent vertices in the graph G, then we say that is a chord. Okay, then a path P is called a monophonic if it is a chordless path. Chordless path is called a monophonic path. Okay, now here just consider this graph. Here we take the vertices V1 and V7. Here identify the monophonic paths. Here we have first identify the possible paths. So the first path joining the vertices V1 and V7 is this V1, V3, V6, V7. Here along this path there is no chord. There is no chord means no two non-adjacent vertices. These two are non-adjacent vertices. Here there is no chord. There is no edge. So this path is a monophonic path. Then if I take the next path as V1, V2, V4, V5, V6, V7. Along this path also, here there is no chord. There is no non-adjacent vertices having edge in the graph. So this is also a monophonic path. Okay. Then if I take the next path as this V1, V2, V3, V6, V7. This is also a path. But here along this path we have V1 and V3 are non-adjacent vertices in the path, but these two non-adjacent vertices have an edge in the graph G. In the path la irukra non-adjacent vertices and the graph la or edge kuduthana adha chord. So this V1, V3 is a chord. Okay, this chord, therefore this path is not a monophonic path. This is not a monophonic path. Similarly, if I take another path V1, okay, V1, V3, V2, V4, V5, V6, V7. Take this path. So along this path we have the two non-adjacent vertices V1 and V2. Along this path V1, V2 is non-adjacent, but this V1, V2 has an edge in G. Therefore this is a chord. So this along this path we have one chord. Therefore this is not a monophonic path. Similarly, we have another chord, this V3, V6. Okay, so here we have totally 4 paths joining the vertices V1 and V7. Out of 4 possible paths, we have 2 paths are monophonic paths and the remaining 2 are non-monophonic paths. Okay, then we have the monophonic distance. So the monophonic distance is defined as the length of a longest UTV monophonic path in G. Here we can define the longest. The length of a longest UTV monophonic path is called a monophonic distance. Okay, from the previous example we can easily identify that every geodesic is a monophonic path. So clearly this P1 is a geodesic joining the vertices V1 and V7. So we have the result is every geodesic is a monophonic path, but if monophonic path, this P2 need not be a geodesic. In this example, P2 is a monophonic path, but this P2 is not a geodesic, not a shortest path. Okay, so you can remember this. Okay, here, okay, suppose here also we take this V1 and V7. Then what's the distance, monophonic distance between the vertices V1 and V7? The monophonic distance is the length of a longest monophonic path. Here we have this is a monophonic path and this is another monophonic path. So the length of the longest, this is the longest monophonic path and its length is 241. So 5. Okay, so the detour monophonic distance from V1 to V7 is 5. Then if I take the vertices V1 and V3, then what's the monophonic distance? Here also we have 3 different paths. First path is this is the shortest path, and second path is this. So along this path we have one card, so this is not a monophonic path. Then another path is along this direction, along this path. This is a path, but this is also not a monophonic path because here we have a card. Okay, from V1 to V3 there is an edge, so this is not a monophonic path. So out of the 3 paths, we have 2 paths are non-monophonic paths, and this is only one monophonic path. So its distance is 1. So D of V1 comma V3 equal to 1. Okay, so in this way we can easily identify the numbers. Okay, so here also we have this D2 distance lies between 0 and P minus 1. So already we have studied 3 parameters: usual distance, D2 distance, and monophonic distance. All the 3 parameters lies between 0 and P minus 1. Then again, we have the result. Already I told you about this. Every geodesic is a monophonic path. From that we have D of U comma B is less than or equal to dm of U comma B. Okay, and again we have this D of U comma B. So this is my cardless path. So every cardless path, the number of edges in a cardless path is clearly less than or equal to the number of edges in a longest path. This is the longest path, this is a cardless path. So clearly the number of edges in this cardless path is less than or equal to the number of edges in the longest path. Therefore we have dm of U comma B less than or equal to this. So we have this chain. So this is a distance chain. Okay, similar to domination chain, here we have a distance chain is 0 less than or equal to small d of U comma B less than or equal to dm of U comma B less than or equal to capital D of U comma B less than or equal to P minus 1. Okay, so here also we have so many parameters. Here the monophonic distance dm is not a metric. Already we have the usual distance and D2 distances. Okay, the usual distance D and D2 distance capital D are metrics. Okay, but here the monophonic distance dm is not a metric. Okay, for that we just consider the example here. Here, what is the monophonic distance from V1 to V3? The distance between V1 and V3 is 1. Similarly, the distance between V3 and V6 is again 1. Then the D2 distance, monophonic distance from V1 to V6 is, okay, so along this path we have the distance is 4. So along the here the monophonic distance between these 2 vertices is 1. The monophonic distance between these 2 vertices is 1, but the monophonic distance from V1 to V6 is 4. So clearly dm of V1 comma V6 is strictly greater than V1 comma V3 plus dm of V3 comma V6. So triangular inequality does not satisfy. This dm, that is monophonic distance, does not satisfy the triangular inequality. From this we conclude that this dm is not a metric on the vertex set V. Okay, so here also we have the definitions. Okay, I think time is over. Okay. Time is nearly 11:30. So we have one more concept, just 2 more minutes. Okay, so next one is monophonic number. So monophonic number, we can define this monophonic set similar to the previous sets. There is previous monophonic D2 set and geodominating set. Okay, and we have the examples. You can verify that one. Okay, so here we can identify the monophonic number of this graph. Okay, so we can easily identify the monophonic numbers. Okay, here we have the results. Clearly the monophonic number lies between 2 and P. Okay, so 2 and P are the bounds of the monophonic number, parameter monophonic number. And again, similar to the previous one, every simplicial vertex of a connected graph belongs to every monophonic set of G, and no cut vertex of G belongs to any G set of G. Based on these 2 parameters, we can identify the monophonic numbers for some standard graphs. We can easily identify the numbers. So there's a complete graph. Since every vertex of a complete graph is a simplicial vertex, so all the vertices of Kp belongs to the monophonic set. Therefore, we have M of Kp equal to P. Similarly, we have the other numbers. So I think with this, I can conclude my presentation. Okay. So you can refer the papers for this. Okay. Now it's the time of questions. You can ask questions. You can ask questions or doubts. Now it's the time of asking questions.
Participants, you're free to ask your doubts now.
Here I have given only the outline of the topics. That's all. Okay.
Thank you, sir, for your clear explanation on distances in graphs.
Okay, thank you, sister.
So I think we can proceed with the vote of thanks, right, sir?
Okay.
Yeah. Let me now invite Dr. Jess Meller, Assistant Professor of Mathematics, to propose the vote of thanks.
Good morning to all. I deem it a great honor to propose vote of thanks on behalf of the Department of Mathematics, Holy Cross College, to our resource person, Dr. Titus, Head and Assistant Professor in Mathematics, University College of Engineering, Nagercoil. Sir, you gave a wonderful session for us. You gave a distance concept, especially geodomination number, vertex geodomination number, detour distance, especially its properties with the examples. Sir, your presentation and explanation were highly motivated all of us to the field of distance in graph theory. Thank you very much, sir, for readily accepting our invitation. Thank you, sir. Thank you.
Thank you, ma'am. Thank you, my friends.
Dear participants, shortly we shall begin our technical session 2. We have with us Dr. Anto Kinsley, Associate Professor, St.Xavier's Autonomous College, Palayamkottai. May I now invite Mrs. Magila, Assistant Professor and one of the organizing secretaries, to introduce and welcome the resource person.
Good morning to one and all gathered here. It's my pleasure to welcome our resource person, Dr. Anto Kinsley, Associate Professor, Department of Mathematics, St.Xavier's College Autonomous, Palayamkottai. Here is his brief biodata for our view. Dr. Anto Kinsley is at present an Associate Professor of Mathematics. He has completed his master's degree in mathematics from St.Xavier's College during the year 1982 and master's degree in technology from Manonmenim Sundarnar University in the year 2011. He awarded his PhD in the year 2013. Apart from his academic positions and credibility, he has served He has served in various administrative positions, such as Vice Principal for Shift 1, Coordinator of Department of Mathematics Self-Financed, and Coordinator of Department of Visual Communication Self-Financed. In total, he has got 32 years of teaching experience. His fields of interest are graph algorithms, flow networks, distance in graphs, central structures in graphs, and distance domination in graphs. He has published 32 research articles in various reputed international and national journals. By the way of intensive research, he is successfully guiding 7 PhD scholars as guide. He also served as a convener of 9 state level, national level, international level conferences. Further, he has completed 2 minor research projects funded by UGC. He was awarded Tamil Nadu State Best Program Officer Award for the year 1994-95. I hope he is apt person for this webinar on distances and algorithms in graphs. On behalf of the Department of Mathematics, I accord you a cheerful welcome, sir.
Thank you.
Thank you, ma'am. May I now hand over the session to Dr. Anto Kinsley.
Respected Dr. Sister Anne Sophie, Principal of Holy Cross College, Nagercoil. Respected Dr. Sister Lima Rose, Vice Principal of the College. Dr. V.M. Arul Flower Mary, Convener and Head of the Department of Mathematics. Organizers, Dr. J.C. Mahila and Sister S. Antin Mary, the faculty members of the department, dear participants, good morning to all. I thank the organizers for the chance to participate in your webinar as a research person. Today I am going to deliver a webinar lecture on graph algorithms and computing techniques. One minute.
Dear participants, sorry for the delay. We'll begin shortly. Dear participants, we shall continue the session after 5 minutes break. Thank you. Yeah, we shall now continue as technical session 2.
Sister, is it visible?
Yes, sir, it is visible. And
Okay,
your
okay.
presentation is visible. Your face is not that visible, sir.
Okay.
Yeah. Yes, sir, now it is, yeah. Good.
Okay.
Yes.
Okay.
Yes.
Thank you. Thank you. Okay. I'm going to explain about the graph algorithms. It is just the introduction part and computing techniques. Computing technique means complexity analysis. So here this graph algorithms. Graph algorithm has the contents like that: algorithms, complexity, orders of magnitude, analysis, efficiency, graph algorithms, types: linear algorithm, polynomial algorithm, exponential algorithm, and NP-complete algorithms, recursive approximation algorithms. First of all, I explain about this introductory part of algorithms. Next, I will explain the distant concepts using algorithm. Finally, I will explain about geodetic sets and geodomination like that. Here, the algorithm and computational complexity. What is algorithm? Algorithm is a finite sequence of instructions for performing an work or a computation for solving a problem. This is a finite sequence of finite sequence of instructions. That's all. That is the algorithm. Then computation complexity means how long it works. The algorithm will work how long. What's the time taken like that. That is computational time complexity that measures the processing time and computer memory required by the algorithm to solve problems of a particular problem size. Problem size means regarding the graph, regarding any graph, we consider the size of the graph. Size of the graph means number of vertices. That is the size of the graph. That is the if we give a graph, we can have a set of vertices. The set of vertices is the data structure. Then, why graph algorithms? Graphs are an ubiquitous data structure in computer science. Networks, LAN, the internet, wireless networks, we use these graph algorithms. Relationship between objects, online dating, social networks, feedback like that. Hundreds of interesting computational problems depend on graphs. Time complexity of an algorithm. The size of the problem is an integer n. The number of inputs. Number of input means regarding the graph, we can consider the size of vertex set n. We measure the complexity of an algorithm, the running time of an algorithm, that depends the size n. Therefore, we can denote this as T of n. Orders of magnitude. For this purpose, complexity purpose, mainly we need these magnitudes, asymptotes. These are called asymptotes. That is big O. First one is big O. Normally we are using this big O. Then big omega, then big theta. There are 5 types of orders of magnitudes, but we concentrate only 3 orders of magnitudes. That is big O, big omega, then theta, like that. Orders of magnitude, big O. What is the meaning of big O? Big O notation. The big O will compare with 2 types of functions, f of x and g of x. The relation between f of x and g of x is mentioned as big O. When you say f of x is equal to big O of g of x, that is, if there exist 2 positive constants, c and k, there are 2 functions, that is, the functions are depending on small x is the variable. Then the 2 functions are, this is a normal case, the 2 functions are related to y. When? What is a circumstance? A function f of x is big O of g of x if there exist 2 positive constants, c and k, such that f of x is less than or equal to c g of x. Sometimes c may be equal to maybe less than, maybe greater than 0. That is in between 0 and 1. That may be fractions. Sometimes c may be a positive integer, like that. Therefore, here positive constants f of x is less than or equal to c of g of x. You can see this is here f of x. F of x for every x belongs to k means there is a bound here. There is a bound k. Therefore, for this k, for k means when you consider this x measuring along the x-axis, here the x comes to this place k. Therefore, when k is greater than k, x is greater than k, then we define f of x. We can calculate f of x and g of x. Therefore, f of x is this is the straight line. Yes, that is given in the geometry. Then g of x, c into g of x is given, is another straight line. You can say after x greater than k, that g of c into g of x is greater than f of x. Then only we can say that this f is related to gx with respect to capital O. Otherwise, f of x is equal to capital O of g of x. Then here c g of x, we can see the examples afterwards. Big O notation. Here f of x is equal to big O of g of x. Here also another example, f of x. This is a curve f of x. Then c g of x is another straight line. After the point k, then f of x is greater than equal to c g of x, where c is a constant. Therefore, we can say that f of x is equal to big O of g of x. Then omega, big O of omega. Here also, there are 2 functions, f and g, f of x and g of x. We say that f of x is equal to big O of g of x if there are positive constants c and k such that f of x is greater than or equal to c of g of x. Then this is just, it is reversal from the big O, because there in big O, f of x is less than or equal to c g of x. Here f of x is greater than or equal to c g of x, where c is also a positive constant. X is also greater than k. Then only we can say that f of x is equal to big O of g of x, omega of g of x. Here another computational magnitude, that is theta notation. Here the f of x, that is f of x curve is bounded by C1 of g of x C2 of C2 into g of x after x greater than after x that is x greater than or equal to k after k. Therefore, here we can say that in this figure C1 of g of x is and C2 of g of x, the two straight lines cover this straight line f of x after x greater than or equal to k. Then only we can say that f of x is theta g of x. Therefore, these are the three magnitudes asymptotes. Then using these three asymptotes, we can find out the complexity. Then other shapes like that, it is L of x, logarithm of x. Here it is a log x curve. Another one is square root x curve. Here also x curve. X curve starts from origin. Okay, and then we can say that there is square root of x curve. Log x curve is bounded by square root of x curve. Square root of x curve is bounded by x. Then here also we can fix this big O magnitude omega and theta. Other shapes, sublinear shapes, polynomial, that is x power k. If x power a, if a is equal to 1, then we can say that it is linear. If a is greater than 1, we can say that it is polynomial. Exponential means x must be in the power. Therefore, here there are four types of curve: 2 into x, x squared, x into log x, x. These are the curves. Next, big O for next, we study about the particular magnitude big O for polynomials. There is a theorem: f of x is equal to polynomial that is x power n x power n plus dash dash a naught, where an minus 1 are real numbers. It is a polynomial. Then we can say that f of x is big O of x power n, because x power n is the leading term, an is the leading polynomial. Therefore, when we can divide this f of x as a power n. If you divide this RHS reconciled by a power an, we can have x power n plus an minus 1 by an, like that. Okay. Then only we can say that it is a polynomial of degree n and also divided by an. So it is, don't worry about this dividing this constant. Then only we can say that this f of x is big O of x n. Suppose f of x is equal to 2 into x power n plus something, then we can say that it is also big O of x power n. Suppose it is 10 x power n plus something, then we can say that it is also big O of x power n. Then example, x squared plus 5x, we can say that it is big O of x squared. Okay, we can forget this 5x also. Suppose it is 5x squared plus x, we can say that this big O of x squared. This is an example. Then now I come to this complexity connecting the algorithm. Adding, it is a very simple program, adding a and b. Input integers a comma b. Okay. Add a, sum is equal to a plus b. Then output is sum. It is a small algorithm, adding just two integer type data, a and b, a plus b. Okay. Sum is equal to a plus b. Here, a and b are given values. Sum is the variable. Sum is equal to a plus b. Then we can have the output sum. Now you see there is only one operation plus works in one time, and so the complexity is big O of 1. Yes. Similarly, there are three inputs a comma b comma c. Sum is equal to a plus b plus c. Then output is sum. There are two operations. There are only one operation. Yet it is used in 2 times. Therefore, the big O of 2. We can say that the complexity is big O of 2. adding n number of integers, the complexity is big O of n minus 1. Adding n number of integers means you can have adding two integers. There exists plus only one plus is used. Plus is used only one time. Similarly, here 2 times, 3 for 2 times. Therefore, here n number of integers, then n minus 1 times plus will work. Therefore, the complexity is big O of n minus 1. We can say that this also big O of n. Therefore, these types of algorithms are linear types algorithm. It is a very, very elementary algorithm. Then algorithm, addition and multiplication. Integers a comma b comma c, sum is equal to a star c plus b star c. There are two operations, a star multiplication and a plus operations. But how many times they are used? 3 times. Here 1 time plus is used, 2 times star, that is multiplication is used. Therefore, we can say that big O of 3, the computation is big O of 3. Input integers a comma b comma c, another one. Here also 2 times plus operation and star operations. Therefore, complexity is big O of 2. Multiplying n number of integers, the complexity is big O of n minus 1 or big O of n. Here it is quadratic. How? Here there are two for loops. One for loop is inside another one. This for loop it will work at n times. Then the outer for loop will work n times. The 0 to n minus 1. Therefore n times. Therefore here the total for loop, the nested for loop will work at n squared time. Therefore we can say that yes, a for loop means inside of these for loops we can have some operations like that, interchanging or plus or minus or multiplication, sometimes like that. Okay. Therefore, big O of n squared. This algorithm has 2 for loops. Therefore, in a step for loop, the cost is big O of n squared because it is quadratic. Then factorial of n, it is a linear type algorithm. How it is linear? Factorial of n means if n is equal to 1, then fact is equal to 1. Else, fact is equal to n star n into fact n minus 1. This is a recursive algorithm. Yes, because you can see n factorial is equal to n into n minus 1 factorial. Therefore, factorial is defined itself. Therefore, we can say that it is a recursive algorithm. Recursive algorithm. It has runtime. How many times this star will work n times? Therefore, this n minus 1 times. Therefore, it is big O of n minus 1 or big O of n. If n has power 1, then we can say that this complexity, this running time is linear. Interchanging. Interchanging means swap a comma b. Here we are going to change a and b itself. B is substituted to a is substituted to b. That's all. Given list 9, 6, 7, 8, 5, then I am going to interchange 5 and 9. Then it is a very, very simple program. It has 3 steps. Swap 9, 5. Yes, that is swap 9, 5 means interchange 9 and 5. Take a is equal to 9, b is at 5. Then first we put the another temporary variable, temp is equal to a. Then only we can put the value for b to a. Then already we can assume the temp is equal to a. Now you substitute this temp variable to b. Therefore, the a and the variable a, the variables, the values of a and b are interchanged. Now the first given list 9, 6, 7, 8, 5. Now the list is ordered list is in increasing order 5, 6, 7, 8, 9. Then measuring the efficiency of algorithms. We have two, if we have two algorithms, algorithm 1 and algorithm 2, that solve the same problem, our application needs a fast running time. Fast running time means how do we choose between the algorithms? Then what is the fastest algorithm? What is the efficient algorithm? How do we choose it? An algorithm's execution time is related to the number of operations it executes. Yes, the previous small problems we have studied about this execution of operations. An algorithm's execution time is related to the number of operations it executes. Then count the number of steps and operations the algorithm will perform for an input of a given size. Number of steps, same one problem, same input data, therefore size is same. Then how the algorithm 1 and the algorithm 2 solve the same problem? Then first of all, we must count the number of operations used and the number of steps used in the two different algorithm to solve the problem, same problem. Then algorithm A requires n squared by 2 steps to solve a problem of size n. Algorithm B requires pi n plus 10 steps to solve a problem of size n. Steps means including the number of operations, including the operations working in how many times, like that, number of times, like that. That algorithm requires n squared by 2 steps to solve a problem. Similarly, the algorithm P requires pi n plus 10 steps to solve the same problem. Then which one would you choose? Now you see that because we are going to test the efficiency. When we increase the size of input n, how the execution time grows for these algorithms. Then if n is equal to, here the two types of algorithm, n squared by 2 and phi n plus 10, then n is equal to 1, then n squared by 2 will give 5. Similarly, when n is increasing, you can see the last column n is equal to 1 lakh. What happened to n squared by 2 and phi n plus 10? Here, this when n is equal to 1 lakh, the execution, you see this execution, it is this is million and million. You can see that when we compare these two rows, the n squared by 2 will require more time. Pi n plus 10 will require there's less time. Therefore, which is good? The efficient algorithm pi n plus 10. Therefore, we can say that algorithm A requires n squared by 2. It is a worst case algorithm. Algorithm B requires pi n plus 10. It is a efficient algorithm. Thus, we can find out the efficiency of the algorithms. Here also, you can see that figure is given here. Step series 1. Series 1 is series 1 and series 2. You can see this is you can see in series 1 the same number. You can see x is equal to 31. The size n is equal to 31. You can see this vertical line. This is more larger than the blue color series. Series 1 is larger than series 2. Therefore, this series 2 is the efficient algorithm. Like that, algorithm A requires n squared by 2 operations to solve a problem of size n. Algorithm B requires phi n plus 10 operations to solve a problem of size n. For large enough problem size, algorithm B is more efficient. Therefore, this is the result. Similarly, we focus on the growth rate. Algorithm A requires time proportional to n squared. Algorithm B requires time proportional to n. Therefore, B is better than A. Efficient algorithm, worst case efficiency and best case efficiency. Worst case efficiency means the maximum number of steps needed. Best case efficiency means minimum number of steps is needed. Therefore, best case and worst case. Here, NP complete problem. A problem is called NP complete. NP means non-deterministic polynomial. If its solution can be guessed and verified in polynomial time. Polynomial time. Non-deterministic means that no particular rule is followed to make the guess. If a problem is NP and all other NP problems are polynomial time reducible to it, the problem is NP complete. Therefore, that is non-deterministic means there exists no rule to frame a algorithm. Therefore, that may be polynomial, that may not be polynomial. Therefore, this is a case. It is a worst case analysis in algorithm analysis. That is NP complete problem. Many maximum number of graph algorithms are NP complete problems. Here, slow sort algorithm. Procedure slow sort. Slow sort means you can see this slow sort as this. This is a working example. This unsorted 23, 78, 45, 8. This original list is given. Then here for the first sort means 23 is chosen. 23 to 78 comparison. Therefore, when we compare 23 and 78. 78 is greater than 23. We are going to sort this list in ascending order. Therefore, 23 and 72, there exists no change. Next, 23 will come and test this 45. 45 is greater than 23. There exists no change. 23 and 8 are checked. Then 8 is lesser than 23. Therefore, using this swap analysis or swap algorithm, 8 is interchanged to 23. First place, 23 is interchanged to 8. That is fourth place. Therefore, after the next one, 23 will go and check 32. There exists no change. Next what? 23 and 56. There is no change because 32 and 56 are greater than 23. Therefore, 23 is kept in the fourth place. 8 is in the first place. This is after pass 1. Okay. Therefore, this testing with 23 is over. Next, 78 is ready to check this. Having a check with 45, 78 to 45, 78 to 23, like that. Next, listen, 23 will be, 23 and 78 will be interchanged. 23 will come to this first place, then 72 in the third place. Similarly, this swap program will interchange this 78 and 23. Then after pass 2, we can have this 23 is here, second place, then 45, 78. Like that, similarly, at last, we can have after the pass 5, we can have the sorted list in ascending order. That is given by that can be done by the sorting algorithm. This is sorting algorithm. First one, you take this R is equal to 1, take this X1, then J is equal to 1 plus 1, that is R equal to 1, 1 plus 1, 2. Therefore, X2 and X1 are checked. Yes, if X1 is greater than X2, then there is a swap. This swap will work. Therefore, it shows that it makes one comparison. We can have n into nc2. We can have nc2 number of operations. Here n minus operation means here comparison less than. This less than is the comparison. This is the operation. How many times it will work? N minus at the maximum nc2 number of times. Therefore, n into nc2 means n into n minus 1 by 2. Okay. Therefore, the number of comparison is theta, big theta of n squared. Here it is n squared minus n by 2. The n squared, the higher term is, all the other terms remaining, the higher term is omitted. Therefore, big theta of n squared. Next, it is easy to imagine that some of these lists are very long. Here it is a very small list, and the replacement of big theta of n squared by an average of big O of n log n comparisons is very, very welcome. Very welcome means we have seen this type of n squared and n log n. Here it is x log x, that is n log n, it is n squared. Therefore, this is n log n is it is efficient than n squared. That is given there. Here, listen. This theta n squared, here also big O of n log n. Finally, we can convert this theta of n squared to big O of n squared by an average of this. Here it is big O of n log n. It is another type of algorithm. Yes, it is linear sorting. Theta of n squared is linear sorting. But we will study about this quick sorting algorithm. Quick sorting algorithm means it has a complexity big O of n log n. An insurance company that wants to alphabetize its list of policy holders will gratefully notice the difference between n squared. This is n is equal to 5, 3 zeros and 3 zeros, 5 million. Okay, then where n squared is equal to this. But n log n, taking log n and multiply this n, we can have this type of values, comparisons. You can check this 25 and add, and 77 and add. Please check that which is larger, n squared is larger. Therefore, this linear sorting is a worst case algorithm where we will study about this type of algorithm. That is quick sort algorithm. Yes. Next, quick sort algorithm is better than this linear sorting algorithm. Quick sort algorithm. This is a quick sort algorithm. This now you can see this quick sort algorithm. Quick sort algorithm means we consider this one, this unsorted, this. You can take this 8, otherwise randomly we can choose 45 or 8 like that. Yes, you can take this 8, choose this 8. Then consider this group. This group means, subgroup means 23, 78, 45. Here, our aim is, we have to sort this 23, 78, 45. Next, we can sort another one, 32, 56. Next, we choose 78 in this group, divide 23 and 45 like that. Therefore, the choosing algorithm means by randomly we can choose this choose the elements, then grouping that left hand side and the right hand side. Then we can have we can sort this algorithm quickly. That example is not given here. Using this algorithm, we can find out the ascending order list. Next, that's all. Elementary graph algorithms. Now we come to this graph algorithms. Graph algorithm means first of all representation of graphs. How do we represent these graphs? Here, 2 standard ways. Adjacency list, that is adjacency list for sports graphs, adjacency matrix for a dense graphs. Normally, we are using dense graphs. Then adjacency matrix. Adjacency matrix, you know that here one it is a given, it is small graph, given graph 1, 2, 3, 4, 5. It is a small graph. Here 1 and 2, adjacency means 1 and 2 are connected. How many times? Only 1. But 1 and 1, there exists no loop. Therefore, there exists no loop. Therefore, 1 and 1 is not connected. 1 and 2, 1 and 2 are connected. How many times? 1 time. Therefore, adjacency. 1 and 3 is not connected. 1 and 3 is connected. Therefore, 1 and yes, in this row you can see yes 0. Below 3 we can see 0 means it is not connected. Therefore, thus we can find out the adjacency matrix. Then graph traverse. Now listen. Graph traversals means these are the algorithms. Yes, algorithms. This old algorithms. We can see these algorithms in any algorithms book for solving most problems on graphs. That is graph traversals for this. First of all, we can visit vertices and edges like that. There are two major traverse algorithms. That is BFS and DFS. They are standard algorithms. We can see these standard algorithms in any book. These are the algorithms. Here the algorithms, there are two types of algorithms. That is what big O of V. V means number of vertices. Here theta of E. E means suppose number of vertices is n, number of edges is small m, then we can have theta of n and theta of m like that. Then there are, when you add these two things, because in this algorithm there are two types of components. First component we need theta of v, second component we need this theta of e. Then adding this theta of v and theta of e, then theta of v plus e. Therefore, this is the algorithm of complexity, big theta of n plus m. Minimum spanning tree. You can have minimum, we use here the spanning tree of a undirected graphs or spanning tree of a direct graph like that. Now, it is an example, laying telephone wire. Here, so many houses and the central office. Direct approach. Here we can connect each house to the central office. It is more expensive, but here you can see this is a graph, it is a tree, then it is connected like that. It is not more expensive. Therefore, it is a better approach. Like that, here spanning tree, how we can generate a MST. MST means minimum spanning tree. In the previous example, we can have the minimum spanning tree. Okay. Here it is minimum spanning tree means it is a graph given, it is not a tree. Then here the minimum spanning tree can be computed like that, A to D, then D to C, like that, E to B. Therefore, it is a minimum spanning tree. For this minimum spanning tree, we can have a Prince algorithm. Just I introduce the algorithms, that's all. Prince algorithm, it will find out the minimum spanning tree. Then all space shortest paths. That famous algorithms we know, Dept algorithm, it will take big O of n plus m log n time. You see this complexity. Therefore, I am giving this example here to analyze the complexities. Then Floyd-Warshall algorithm, this is another algorithm to find the shortest path between two vertices. Shortest path between two vertices. Therefore, here it is Floyd-Warshall algorithm. We need big O of V cube. But it is Dept algorithm is better than this Floyd-Warshall algorithm. That this algorithm, what is the work of this algorithm? It will find the shortest distance between two vertices. Then finding a maximum independent set. Maximum independent set means here, maximum independent set means a set of vertices is called independent if no pair of vertices is connected. Then we consider this ADIH. ADIH means here it is D, okay, ADIH. ADIH is an independent set, but it is wrong. It is not an independent set because these two I and H are connected. Here ACJFG, ACJFG. It is a maximal. It is a independent set. Then we can say it is a maximal independent set. Maximal means the cardinality of this set of vertices is maximum. Then only we can say that it is a maximal independent set. Then what is our aim? We have to find the maximal independent set of this graph, set of vertices of this graph. An independent set is called maximal if by including any other vertex not in I, the independence property is violated. Suppose we add one more vertex, it is not in the maximum, not in the independent set. We add this. If it is affected, if it is violated for independence property, then we can say that it is a maximal independent set. Here is a maximal independent set. Here is a problem when we are going to find out the cardinality of maximal independent set. There is a connection between independence, maximal independent set and the dominating set. Domination number and maximum independent set number, we can have one connection. Here we see domination problem. Every maximal independent set is in a graph G is a minimal dominating set. Minimal dominating set, that is minimum of all minimal dominating set is called the number is called the domination number. Therefore, here we find out here a theorem. Every maximal independent set in a graph G is a minimal dominating set of G. Therefore, the cardinality of a minimum dominating set in a graph is the domination number of a graph. That is the definition for domination number. Using the algorithm to find the size of a maximal independent set, we can design a 2 minus epsilon approximation algorithm. We can say the approximation algorithm. Now I am going to discuss about this approximation algorithm. That is maximum independent set. Maximum independent set, it is a very simple example. C5, 1, 2, 3, 4, 5 are vertices. Then you can see 1 and 3. 1 and 3, 1, 3 is a maximal independent set. 5 and 2, 2, 5 is a maximum independent set. If you add one more vertex, then it will not be a maximal independent set. Suppose 1 and 3, 1, 3 is a maximal independent set. You add 4, what happened? Then 4 and 3 adjacent. Therefore, it will not be a maximal independent set. So similarly, you add 5. Therefore, 1, 3 is a maximal independent set. 2, 4 is a maximum independent set. 3, 5 is a maximum independent set, like that. Therefore, we can say that the cardinality of maximal independent set is, cardinality of maximal independent set is 2. How do you find this? Now I am going to use this algorithm. First of all, I delete 1. Any vertex. Therefore, delete 1, we can have a path that is a polynomial 2, 3, 4, 5. It is in the left-hand side. You put this in the left-hand side. Next, we delete the neighborhood of 1. Arbitrarily, we have chosen 1. Now we delete the neighborhood of 1. Therefore, 2 and 5. Here, delete 2 and 5 from this curve. We can have a single edge, 3 and 4. Next, it is now I am going to use this recursive algorithm. Next, you choose this. In the place of this C5, we can have a polynomial phi4. Okay. Next, I delete 2. Arbitrarily, I choose these 2. Yes, okay. Then we can have delete this 3, 4, 5. Next one, we delete the neighborhood of 2 also. Therefore, here we delete neighborhood of 2 also. That is 3. We can have 4 and 5. This is another edge. In the right hand side, you see, in the right hand side 3, 3 and 4, it is a P2. Therefore, now we delete 3. We have a singleton vertex, therefore A. Then you delete this neighborhood, we can have pi. In this side, we can have pi. Therefore, here, left hand side, another part, here the left hand side, we can have this curve. Then this also is splitted into 2 curves, left and right. Here, this also splitted into, right hand side also splitted into 2 curves like that. Finally, here it is final. In the left hand side, we can see this final, that is 5 only. Here also, you can see in this place 0, because 0 element pi. Yes, we will go to the algorithm now. Yes, maximum set 1. Algorithm name is maximum 1 set 1. Return the size of largest independent. Therefore, what is our aim? To find the size of the largest independent set of maximal independent set of vertices of G. If G has no edges, suppose there exists no edges. No edges means 1, 2, 3, 4, 5. No edges. What is the maximal independent set? All the vertices. The 1, 2, 3, 4, 5. Therefore, the size is the cardinality equal to 5. And therefore, we can say the cardinality is equal to 1. If G has no edges, maximum set 1 is equal to the whole vertex set cardinality. Therefore, else, suppose there exists vertices having edges, then else means there exists vertices having edges. Then we can choose some non-isolated vertices V star of G. Delete this. We choose some non-isolated vertices V star. Here also in this graph, there are 5 edges. Therefore, the first obvious case is not satisfied. Then we can choose some non-isolated vertex set. Here we choose this one like that. That is given in the algorithm. Choose this V star. V star is equal to 1. Therefore, max set 1, G minus V star, G minus 1, the vertex 1. Then we can have this 2, 3, 4, 5 like that. Therefore, similarly, the last here, what is the definition of N1? Definition of N1 means G minus V star, find the maximum set 1. Therefore, cardinality of maximal independent set, largest independent set is G minus V star. That you put this is as N1. Then neighborhood, in the right hand side you can see this has the same, we are applying the same algorithm. We can have the N2 values. Therefore, left hand side N1, right hand side N2. N1 and N2. Then find out this maximum of N1, then N2 plus 1. Here in this program, finally we will have this N1 is equal to finally means here it is, we can take this only, because here N1 is 2, N2 is equal to 0. N1 is 2, N2 is equal to 0. Here it is also, here it is N1 is equal to 1, N2 is equal to 0. Then finally, applying this program, this algorithm, we can have N1 is equal to 2, N2 is equal to 1, 1 plus 1. Otherwise, N2 is equal to 0, then 1 plus 0. What is the maximum value? Maximum of N2, 1 is N2. Therefore, in this C5, we can have this cardinality of maximum independent set is is 2. Similarly, this is the complexity result. Complexity result means we use this recurrence relation. After this recurrence relation, we will have this xn is equal to big O of C plus epsilon power n. Finally, we will have Fn is equal to big O of 1.619 n. Normally, when normally we can have the complexity of this algorithm is Fn is equal to big O of 2 power n. Big O of 2 power n. Normal case. That is worst case algorithm, we can have this. Here, this algorithm, choosing this one vertex arbitrarily, then deleting it, then next one is in the right hand side, delete this neighborhood also, like that. We can have Fn is equal to big O of 1.619 power n. Then, next maximum set algorithm, this is a second algorithm. Using this, choose a vertex V star of degree greater than or equal to 2. There is a change from that algorithm and maximum set 1 algorithm and maximum set 2 algorithm. There is a change. Then after that, using the same recurrence relation and finding this, we can have 1 point big O of 1.47 power n. Yes. Now listen, the previous one has cardinality, previous one has the complexity, big O of 1.619 power 9. Here it is big O of 1.47 power n. The worst case is very simple algorithm. We can find this maximum set. Worst case is big O of 2 power n. Big O of 2 power n. 2 power n. Therefore, the complexity is reduced from 2 power n to 1.619 power n and 1.47 power n, like that. Finally, 1.39 power n also can be obtained. Yes, it is regarding the data input. Data input means regarding the graph. It is a very big graph. We can go to this also. Big O of 1.39 power n. Therefore, we can say that the complexity is approximated to big O of 2 power n to big O of 1.39. This is called, this algorithm is called, this running time is reduced from 2 power n to 1.39 n. This is a reduced algorithm. This is called approximated algorithm. This is the complexity is approximation. Therefore, approximated algorithm is this. We can say that this 1 point, you see this 1.619 power n. That is 2 minus something, some very small number. That may be epsilon. Therefore, this big O of 1.619 power n can be called as big O of 2 minus epsilon. Therefore, this case can be rewritten as 2 minus epsilon approximation algorithm, where epsilon is between 0 and 1. In many algorithmic articles, we can say that we can see 1 plus epsilon approximation algorithm or 2 minus epsilon approximation algorithm. This is the case. Then domination problem. Every maximal independent set in a graph G is a minimal dominating set of G. This is a result relating the independent set and the dominating set. Cardinality of a minimal dominant set in a graph is a domination number. Then we can say that Yes, still now the algorithm for finding finding the domination number is NB complete. Understand? Now here we can say that this can be reduced using the maximal independent set algorithm. This domination number can be found using 2 minus epsilon approximation algorithm. It is a very, very important thing. Next, distance in graphs. Okay. We can design various types of algorithms for central structures like center, median, centroid, central path, or like that. We can design various types of algorithm for the above central structures using detour distance. Detour distance means detour center, detour median, detour centroid, detour central path, like that. But these types of central structure using this detour distance have not yet studied. Therefore, researchers can study this type of detour distance, then study framing some results about detour center, detour median, detour centroid, like that. Then framing algorithm for the detour concepts in central concepts using detour distance. Similarly, we can design various types of algorithm for the above central structures using monomorphic distance. The references, Chartrand, it is a very good book, Chartrand and Applied and Algorithmic Graph Theory. Next one is Wilf. Wilf is it is a very standard book, H.S. Wilf, Algorithms and Complexity. Yes, here it is a very good book for domination and central concepts. That is, the third one is a very good book because Peter J. Slater is originated the central concepts using detour distance.
Thank you very much, sir.
Sister, time aidicha? Stop
Yes,
panniralama?
yes, sir. Yes, sir.
One more thing, please wait. Please wait.
Yeah, yeah.
I have so many material to display, but because of time, I want to finish this. I prepared for these geodetic concepts in graphs like that. Yeah, any researchers or any students can approach me using this. This is my mail address, antokinsley@yahoo.com. This is my mobile, 944344646. Anybody can approach me, then I will help you. Okay, thank you.
Thank you, sir, for explaining the procedures of computing algorithms with ease and expertise.
Okay.
Dear participants, you are now free to raise your questions and clarify your doubts. And one more information. Remember to fill and submit your feedback form, which will be posted shortly in Meet as well as in YouTube to receive your e-certificate.
I thank all participants and all organizers. patiently listening my talk. Thank you very much.
Thank you, sir. May now invite Dr. Sujin Pla, Assistant Professor, to propose the formal vote of thanks.
Good afternoon, everyone. Gratitude is when a memory is stored in the heart and not in the mind. Moving on to the close of the session, I take privilege in thanking each one of you who actively participated in this webinar. First and foremost, I thank the Lord Almighty for the successful conduct of this session. With due respect, I record my heartfelt gratitude to Dr. Sister Gerardine Jayam, the Secretary, Dr. Sister Annie Perfect Sophie, the Principal, Dr. Sister Lima Rose, the Vice Principal, and Dr. Vinolia Josephine, the Controller of Examinations, for the sincere efforts they have been taking and rendering their support in all the activities of college. I extend a sincere and warm gratitude to you all, dear sisters and dear ma'am. Next, I express my sincere thanks to the resource person of this session, Dr. Anto Kinsley, Associate Professor of St.Xavier's College, Palayamkottai. He has given us an in-depth idea on graph algorithms and computing techniques with utmost clarity. I hope it would be very useful for researchers. Thank you, sir.
Thank you.
I would also like to convey my sincere thanks to Dr. Titus for his intellectual talk on the distance in graphs. And with a heart brimming with gratitude, I thank Dr. Arulflower Mary, the head of the department, organizers of this webinar, Sister Antin Mary and Miss Mahila, and all the faculty of the PG and Research Department of Mathematics, Holy Cross College, for their scholarly suggestions and support for the successful conduct of this webinar. And dear participants, I thank each one of you for your active engagement throughout the session. To plant a garden is to believe in tomorrow. Let's log out of today's session with the hope that we will meet again shortly. Thank you. Thank you, one and all.
Life is a math equation. In order to gain the most, you have to know how to convert negatives into positives, says an unknown author. This marks the end of the webinar. At the end, I would like to thank everybody for being there with us. Your participation is highly appreciated. You shall receive a participation certificate once you submit the feedback form. Thank you and have a great day. Thank you, sirs.
Thank you.
Sister Mahila, thank you. Thank you. It was very nice.
Thank you, ma'am.
Okay. ஐஸ்வர்யா இங்க ஒருக்கா வா மக்களே.